Hello everybody. Let us start our discussion today. Today we'll discuss one of the famous solution of the Einstein's equation, and this is the first solution of the Einstein equation came in the year of 1916. In the same year Einstein wrote down the Einstein's equation. So this is a vacuum spherically symmetric static solution. So let me first go through them one by one. What do I mean by vacuum solution? So by vacuum solution, I mean in the region where I want to calculate the solution of the Einstein equation, which is a metric. So in the region of space-time, of course, where we want to solve this, where we the solution, in that place, T alpha beta is 0. So that is what I mean by vacuum. Then I said that it's a spherically symmetric solution. What do I mean by spherically symmetric? It means that the distribution of matter is symmetric with respect to a point. The distribution of matter which is creating this solution, and see where we said that vacuum solution, I said in the region where we are interested in the solution, the metric, there in that region there is T alpha beta equals to 0, but there can be something in somewhere else which is creating that metric at that particular region. So what we say here is that the distribution for which this solution is over the entire space and time. Is spherically symmetric. Or sometimes it is also called centrally symmetric. There is a center. There can be non-zero velocities. It is not that all the matter is at the same, is always, it doesn't move. There can be a velocity component also for the matter, but the matter has to move with velocity such that the velocities are also always radial. If there is in the matter density. So this is also spherically symmetric and the velocity is radial. So the kind of thing that you can think of is a sphere. The radius of the sphere is changing with time. If you see the sphere from outside, then with respect to the center of the sphere, it still remains spherically symmetric. All the parts of the sphere are going out and coming back in at the same time. There's a catch in that sentence, so you should think about it, but I'll leave it there. Now, whenever I say that this is spherically symmetric, it implies that the space is no more homogeneous. Homogeneity in of the space is broken. So there is one point which is spatial in the space with respect to which everything is spherically symmetric. So there is one important point in the space. So the homogeneity is broken. I cannot choose the origin anywhere and see the spherical symmetry. And then I said that the metric is supposed to be static, which essentially means that the metric components is independent of time, the coordinate time. Okay, now it turns out if I have a spherically symmetric static vacuum solution of the Einstein equation, there is only one such solution possible, and it's called, there is a theorem called Wickoff's theorem, which will not go into proof, or I will just state it, even not write it, which tells you there is only one solution, which is the famous celebrated Schwarzschild solution. One thing you should remember that one thing I should mention to you is that obviously this solution can be arrived at a very, from all the assumptions that we have talked about from the first principles. I'm just not doing it here because of the time limitation in the course. I request you to go through the derivation given in the famous book by Landau and Lifshitz, and it's a very straightforward derivation. You should be able to follow it clearly or easily. So let me write the line element here, which is ds square is 1 minus rs by r. I'll define what is rs. Let us write c square dt square instead of writing just dx0 square. And it's a spherically symmetric. So the spatial part has three coordinates. We choose them r, theta, and phi. And it's obvious that r equals to 0 is this point of symmetry. To the power minus 1 now, dr square minus r square. Let me write it this way, and I will mention here that d omega square is the line element on the surface of a sphere, of a unit sphere, and rs is 2gm by c square. M is supposed to be the mass of the body of which this solution is, and obviously we are not looking at a place where t mu nu equals to 0. We are looking at a place there is no mass, but outside the body, massive body, this is the solution. This is called Schwarzschild radius. We'll see that it plays a very important role in this solution. So let's analyze this solution a little bit before we go ahead. First thing, you realize that the asymptotic limit of this solution, which asymptote that we are talking about, r tends to infinity asymptote. So at r tends to infinity, you see that rs by r, rs is finite of course, so rs by r goes to 0. So metric becomes g alpha beta tends to the good old Minkowskian metric, which is a very nice thing that this goes to Minkowskian metric at r tends to infinity, which essentially means that if you go very far away from the spherically symmetric body, which is producing this metric around it, then you don't see a an effect of the body. You just see a simple flat Minkowski metric, which is very convenient. Then you can say that if you are sufficiently far away from the spherically symmetric body, we will not feel any effect of its gravity. And that we know that sufficiently far away from any massive body, you don't feel its gravity. In Newton's mechanics of gravity, Newton's laws of gravity, the force is 1 by r squared. R very large, the force is 0. Now, this metric, so I have not written the metric explicitly, but you can imagine what is the metric looking at the line element. G00 component is 1 minus rs by r, G11 is its inverse, and the G22 is r squared, and G33 is r squared sine squared theta. So as simple as that. So if we ask the question, the singularities in the matrix where the metric components blow up. So we see that there are two singularities. One is at r equals to 0. At that singularity, what happens at r equals to 0? Well, at r equals to 0, G00 and G11 has problem. So this is the singularity of the matrix, and it can be shown this is a real singularity, which means that if I change a coordinate system, this singularity does not disappear. This is a singularity of the system. At r equals to rs also, there is apparently a singularity, because if I put r equals to rs, then G11 becomes 1 by 0, which is not very good thing to have. So this is an apparent singularity. I call it apparent because if you can choose coordinate systems where you can show that this singularity actually does not exist. If you calculate the curvature scalars, not the Ricci scalar, but other curvature scalars, you will see that they are quite finite at this r equals to rs. The Ricci scalar will be 0 because it's a vacuum solution. All right, if we look at the spatial part, so the spatial part of the metric is a little bit different from what we have in spherical polar coordinates. So this is dl squared and spherical polar coordinate for normal Euclidean geometry. Let me just write down the d omega square here. Right. So this is the spherical part. And if I consider now that I will only move radially, we can ask the question that how much distance do you move if you move radially from 0 to r? That may seem a very silly question because I'm moving radially. If I move a distance, if I go from the coordinate value of 0 to coordinate value of r, I should be moving a distance r, right? But not quite so. You can see here, so radial movement or radial distance essentially mean in this case I will say d theta and d phi equals to 0. So the distance traveled dl, if I integrate it 0 to L, so that is nothing but the distance traveled. So that will be, so let's call this L0. For that, I have to integrate this, and it should be minus 1 inverse here. And actually take a square root and dr. So that is how much distance you have traveled. You have to integrate this from 0 to capital R. So see the distance you will get in terms of rs, of course, because I can always write this as rs. But this is not the same distance as 0 to r or capital R. It's a different distance. So you can imagine now that if I go around in phi direction once, I will go around by a angle 2 pi, and you can show if I do the integral on the phi direction, I will get a length which is 2 pi r. But in this particular case, 2 pi r by L naught is not 2 pi. It's something else. And that is where you see that there is a non-trivial geometry here. Let's look at the relation between the coordinate time and the proper time. So relation between coordinate time, which is the dt here, and proper time. Well, I considered that the movements are d theta and d phi are 0. Let's consider that. That will just make our life easier to work with. So what will I get? Well, ds square is c square d tau square, where tau is the proper time, which is now equals to 1 minus rs by r Obviously, when you are measuring the time interval, you should measure at the same point. So dr is also equals to 0. So it's a time-like interval. It's not cannot be a space-like interval and start measuring the time there. Now, what I see here is that d tau is 1 minus rs by r square root of that times dt. Because 1 minus rs by r is always less than r, d tau is always less than or equals to dt. In fact, if r equals to infinity, then these two are same. Otherwise, one is d tau is always less than dt. So we will always require smaller amount of time by the observer who is measuring the time. So that's the proper time. The proper time between any two events will always be smaller than the time measured in the coordinate by the coordinates. So the coordinate time will be larger always. Next, what we'll try to look at are the geodesic equations. Now, you know how to write down the geodesic equation, and this metric was in your exercise, so you should be able to write down the geodesic equation. Straightforward, I will not do the math here. I'll just write down the geodesics. There will be 4 of them because you are dealing with 4 dimensions, and I will consider the parameter I will consider to be lambda. We can set it to tau whenever we want, but we will consider it lambda in general because then the equations that we'll write down will also work for light-like geodesics. Okay, so d2t d lambda 2 plus, this is the first equation that we are writing down, and let me put in the c square here. I will only write down the r equation because these are the 2 equations which I will be needing for the rest of the calculations. you can write down the other equations later. So this is the equation corresponds to x naught. This is the equation corresponds to x1. x1 in this case is r. This equation is rather a little big. Please do the calculation and find out the Christoffel symbols for this metric and non-zero Christoffel symbols, and then re-evaluate this equation, the geodesic equations. You need to make your hand dirty doing some calculations if you want to learn GR. The formulation of GR is quite easy, but the calculation sometimes is trivial. But then when again the physics comes out of it, they're really beautiful. Okay, so I am not writing down the other two equations, which are for x2, which is theta, and x3, which is phi, partly because you will not use them, but you should try and write down. As you can see, the things has become already very complicated. The second equation on R is extremely large. Can we make them simpler? We can, and that's why we have learned about the killing vectors. So let's look at the symmetries of the metric. And this one has a lot of symmetries. And we'll address them one by one. The first thing you realize is that the entire thing which I write as ds square, which is g, say alpha beta, dx alpha d lambda dx beta d lambda, if I call it d lambda d2 as d lambda 2, this thing is constant. If lambda was tau, it is just c square. So we'll call this epsilon. Epsilon, where epsilon is just c square if lambda is tau. This is the case where I'm talking about the trajectories of the geodesics of massive particles. If it is massless, which is the trajectory of light, and for the trajectory of light, we know ds square equals to 0. So in that case, epsilon is simply 0. Okay, so that is one. So epsilon is a constant. So these are invariants or constants. So which means that now I have already one constant, and so I can use this because dx alpha, d lambda, etc. looks like quite familiar things, which I have written one here, dt by d lambda whole square. That is when x equals to 0, alpha equals to 0, and beta equals to 0. Okay, scaling vectors. Now, it's a spherically symmetric metric, and we all know that the angular momentum is supposed to be conserved. And the angular momentum, if it is conserved, we know that we can choose the direction in which we will work on. So the theta direction can be chosen because every motion happens in a plane. So angular momentum is one of the conserved quantity. Its direction is conserved. Angular momentum is a kind of vector. Its direction is conserved, which implies that I can choose a suitable theta. So these motions happen in plane, all motion happen in plane. This is just like central force. Same reason, there also motion happen in plane. In fact, you will see this is just like a central force. So I can choose theta equals to pi by 2, and immediately many of the equations will simplify. Like for example, here I have sine square theta. If theta equals to pi by 2, this will just be 1. If I consider the magnitude of the angular momentum, so I have chosen the theta direction. I can to fix the magnitude of the angular momentum, I can write a killing vector, which is so I was writing with xi, so let me write with xi. So I have a killing vector which will preserve the phi component, and if I write the corresponding components of the one form, what will it be? So it 0 0 0, and then I have to multiply it with a g minus 1. I have to multiply with g phi phi, and g phi phi is nothing but minus sine square theta r square. Now sine square theta is just 1, so this is nothing but r square. And what does the conservation laws say? The conservation laws tells you which we learned last time, tells you that epsilon mu, p mu is conserved. Let us call this conserved quantity L, which is the angular momentum essentially. And what is this? So this is r square, and p mu is nothing but d phi d lambda. So r square d phi d lambda is L. So wherever I will see d phi d lambda, I can now substitute that with r square. What else do I have? Well, remember, it's a static metric. So another concept quantity is that the metric is independent of time. So the another killing vector will be a time-like killing vector. So let me just write it down. So this will be, I can write this as, I'm sorry. So yeah, so no, it's all right. So epsilon mu, and epsilon mu upstairs will be 1 minus rs by r, and then rest of it is 0. So the conserved quantity here, if time is conserved, if time is, the metric is independent of time, the conserved quantity is supposed to be related to energy, because remember that if your Lagrangian is independent of time, energy is conserved. It's actually a similar thing happening here. So that's the P0 component, right? And how do I write that down? Well, so this is C dt d lambda. This is the zeroth component of the velocity times epsilon mu, which is 1 minus rs by r. This is conserved, so this I write as root over 2e. This is just another constant. So this is what I have from the conservations. I have got this. I've set theta equals pi by 2. I have the geodesic equations. Now let us see what else do we have. We have this equation, which we'll now write explicitly, g00 dt d lambda, etc. So if I write that, let's see what we will get. So g00 is 1 minus rs by r, and then c square dt d lambda whole square minus G11 is minus 1 minus Rs by R inverse, and then I will get d or d lambda here, square of that. Then the next term is minus R square d theta square, but remember that we have constrained our motion in the theta equals to pi by 2 plane, so theta doesn't change in that plane, which means that d theta is 0. So I am left with the last term, which is minus R square d phi d lambda square, and this is, as we defined earlier, is epsilon. What we are up to here by doing the trajectories calculations is that we want to see how the trajectory of the particle will be around such a solution, around a body which has such a solution. Okay, that's what our goal is. So let's see what we can do. Well, dt d lambda I can replace from the previous line, where c dt d lambda can be replaced by, or c dt d lambda whole square can be replaced by 2e by 1 minus rs by r square. So let's do that. And 1 minus rs by r will become into the denominator. So I'll get 1 minus rs by r to the power minus 1, and simply 2e here. Let's keep dr d lambda as it is. Dr d lambda looks like the normal radial velocity. And d phi d lambda I can replace with the definition of angular momentum. So d phi d lambda whole square will be L square by r to the power 4. So I get here L square by r square, and that whole thing is equals to epsilon. Now this looks more like a velocity term. So I'll rearrange this a little bit, and let me write down what do I get after the rearrangement. So I get half dr d lambda whole square plus So I get this very simple looking expression, and this I can make look a little more familiar for you. Just let us consider. Let's first write this entire thing as V effective, which is a function of R, of course. And V effective as a function of R is 1 minus Rs by R into epsilon plus L square by R square. So if I write it this way, then you see that this expression looks very familiar now. It's like dr d lambda whole square into half is like the kinetic energy plus an effective potential energy, which is a function of R only, equals to total energy. And it has this form, which is a very, very familiar form to us. Of course, it's not dr dt square, but this is a type of equation that we have also seen when we were analyzing the central force, and I shared a lecture with you where it was done quite elaborately. So I hope that you have gone through that once, and that is what is this about. Okay, so first For to analyze any further, let us look at trajectories of massive particles. We have not done any approximation yet, so that one should remember that we are dealing everything exact. So trajectories of massive particle is what we want to look at. And for the massive particle, you remember that epsilon is nothing but c squared, and lambda we can take to be tau. So this equation simply becomes half dr d tau, now looks more like velocity, whole square, plus v effective r, of course we will do the replacement in that, equals E. And now let us write V effective R explicitly for this particular case is half 1 minus Rs by R epsilon plus L square by R square. And I forgot to substitute epsilon. Epsilon, if you remember, is C square. It will also be good if I can actually write these everything in terms of dimensionless quantities. So let's do that. So let us write. So this is things in terms of dimensionless. This is very useful for doing any computation, analytical or numerical, where you identify length scales and time scales of the system and make everything dimensionless. And that's what you're going to do here. So we write a V, so let's say this way, V effective, which is a function of something we call capital R, is defined shortly. This is just 2V effective by C square. V effective is supposed to have the dimension of energy per unit mass. C square is essentially energy per unit mass. So this is V effective weighted by half C square essentially. We defined capital R to be obviously R by Rs, and we defined small l to be capital L by Rs times C. You see, small l has kind of its moment of the velocity. So moment of the velocity is length times c. So small l is also dimensionless. So in terms of these dimensionless quantities, let's see what V effective has become. This is in the dimensionless form. And let me open up the bracket. This is 1. One by R L square by R square L square by R cube. Let's see what was the Newtonian case. This is just to compare. In the Newtonian case, V effective, if I write in the case of Newtonian, so let me put an N here. This will be, you can check with the lecture you have, it will be this much. So I have two things extra. One is a simple one, and the other is this L square by R cube term. Okay, so there are two extra things here with respect to the Newtonian. If you look at the V effective and calculate the extrema of V effective, that is a good way of knowing how V effective looks as a function of R. You can just use a computer nowadays and plot, but this is also a good method. And give you more insight, of course. So this is 1 by R squared minus 2L squared by R cube and plus 3L squared by R to the 4. If you want to find the location of the extrema in terms of capital R, what all you have to do is you have to set del V effective del R equals to 0, and you get the location of the extrema as the following. This I am skipping the calculation. You should be able to do it. This is very straightforward. So this is, there are two extremas, as this is a quadratic equation. You can see the quadratic equation has two solutions. So these are 2L squared and 3 by 2. There is an approximation going on here. So I just put that tilde sign. The two extremas, which is 2L squared and 3 by 2. If I go back to the original notation, remember that R equals R by Rs equals 2L square. L square is L square by C square Rs square. This implies this happens at R equals 2L square this is one case. The other case, R is simply equals 3 by 2 Rs. Okay. Let me try to plot these equipotential. Let me try to plot these potentials. And let me try to plot this for a given R. Sorry, given value of L. So this is R. In this case, here I am plotting V effective as a function of R. So a sufficiently large L, it looks like this. So there is a maxima here and there is a minima which corresponds to these two solutions. Okay. If I try to plot the corresponding thing for GR, sorry, for Newtonian gravity, it looks like this. Obviously, they doesn't have the same values of L, etc. But the curve looks like this, which has a single minima here. That minima is shifted in this case. I mean, these two minima you can consider, change the parameters to make them similar also. So this is a place where I have a stable circular orbit. Here also, I have a circular orbit, but it's an unstable circular orbit. In the Newtonian case, you see that there is a centrifugal barrier which cannot be crossed by the particle. But in case of the Schwarzschild gravity, so you see that if a particle has energy which is above the height of this barrier, then the particle can go inside, and there is nothing which will stop the particle to fall to r equals to 0. I hope you understand these curves readily. I did not explain why I am plotting and what I am plotting. If you go through the lectures on the central force, this will be quite clear to you. If it is still a problem, please come back to me. Okay, so let us talk about what happens in case of massless particles. So photons are the massless particles. They're not attracted by gravity because they don't have mass. Newtonian gravity only works for mass. Now for the massless particle, what all will happen is that in that V effective, epsilon will be 0. So this epsilon I have to set as 0. So I can again write a V effective as a function of r. So if I play the same dimensionless trick, so this will be L square by r square minus L square by r cube. And you immediately realize that this can have a minima, because it's 1 by r square minus 1 by r cube essentially. And if you calculate del V effective by del r, set this to 0 to get the extremum, and the extremum will not be a minimum, it will be a maximum. This will be equals to 3, which is the radius small r is 3 rs essentially. Ah, 3 by 2, I'm sorry. Right, so how does the potential looks like? Effective potential looks like in this case. So in this case, this, as I have written, it will be an extremum, maxima that you can check. So it will look the following. So this is r, and I'm plotting P effective as a function of r. It will look something like that. So there is an unstable circular orbit here, and you can see if a light ray now has energy which is energy and angular momentum such that the E is here for that light ray, there is nothing that will stop it to fall into the system. For any other E, it will just bounce back from there, any lesser E than that height of the potential. So this is essentially the orbits, or how the orbits look like, you can get from here. One thing you have to remember is this is just an effective potential, so we are talking about the r coordinate only. To see what happens to the phi coordinate, we have to look at this expression L equals to r squared d phi d lambda. So if you incorporate that, you will get the total trajectory. And there are different types of total trajectory. Because all of you have done enough computational physics, I'll request you to figure out what these trajectories are. I will not talk much about the other properties of the Schwarzschild black hole. See, we have seen a few things here. We have seen that the centrifugal barrier does not exist. Given, okay, so that is a catch here. So we are writing down an exterior solution, and we have not said what is R equals to Rs, which we'll say shortly. But if the object, the spherical symmetric object which is creating the field is greater than, if the radius of that is greater than R equals to Rs, then the centrifugal barrier will exist, because then you can think of that the if the radius of the object comes up to here, then the potential will almost look like a potential for the Newtonian case. And that's the case for example, sun. There will be small change, but very small change, which will not be even seen much by the planet like Earth, but the Mercury it will be seen. But in case the object is compact enough, dense enough, then you will start to see these bizarre things like there is no centrifugal barrier. So whatever be the angular momentum, if you can have enough energy such that particle falls in. And then you realize that there are non-trivial trajectories for the light rays. The light rays do bend, they do get attracted by the object, and they can fall into the object if their energy is higher than a certain energy. Let's ask the question. Let's ask a different question now. How long does it take So how long an observer take to reach r equals to rs from infinity? Well, so if you want to calculate this, one should calculate this in the proper time. So this is the clock of the observer. We started from r equals to infinity and coming towards r equals to rs. And that clock, how much time will it measure? How will I know that? Well, the way I know is that I know dr, the equation dr d tau whole square is equals e minus c square by 2 1 minus r is by r. Where do you get this equation from? Here, by setting L equals to 0. I'm setting L equals to 0. Why am I setting L equals to 0? These two equations combined. Because I'm talking about a radial trajectory. Okay. So how do I calculate the proper time d tau? Now will be, so if it has elapsed this much amount of time, now I have to integrate from infinity to rs. And this integration is dr by root over and I can see this integration is quite finite. Even for example, if I choose e equals c square by 2, then this integral just becomes integral minus infinity to rs dr by root over which is a finite integral. If you calculate, you will see that you will get a finite value. So the observer, when he looks at his clock, he takes finite time to fall from r equals to infinity to r equals to r. But what about the coordinate time? An observer who is not falling with this person, but trying to measure. So, like you are falling into the black hole from r equals to infinity to r equals to rs. I just said black hole because that's what the Schwarzschild solution is, but we have not studied any much property of such a black hole. So I restricted myself for from telling you that, but just mentioned you. But anyway, so it is falling from infinity to rs, r equals to infinity to r equals to rs, and some other observer is watching that. So how much time will he see if this observer takes? Now, this external observer will certainly look at a clock which is associated with him, its time measurement associated with him. It is nothing but the coordinate time. So I have this equation now, which we used a little while earlier. From the time like Killing vector, it came out. And I can combine this with this, where I replace d tau square with dr square. And I can write now how much coordinate time is spent as the object falls. And I'm not writing it explicitly, but you can see it will be some function of r again and dr. And you will see that this will come out to be infinite. Just try to do the math, it is easy to see. Once it comes, so what you realize is that you will never see that observer is falling towards the r equals to rs, the Schwarzschild radius. For you, he will never reach the Schwarzschild radius, but he will actually go past the Schwarzschild radius. That is something which is bizarre happening at the Schwarzschild radius. For all external observer, it looks like a boundary which these observers cannot cross because they can only asymptotically fall to that. So that's why it's called special Schwarzschild radius. I will stop here. There are a lot more to say about the black hole, but all of that you can imagine is beyond the scope of this course. I request you to go through the chapter on spherical symmetric body or black hole in Landau-Lipschitz. It's essentially is an excellent read. Thank you.